Welcome back everybody to lesson 17 of the Dead Earth game development series. I'm Gary Simmons of the Game Institute. I've also got a personal channel here on the Game Institute, so if you fancy subscribing to that, I'm going to be posting lots of juicy development videos that I find on my travels, as well as letting you know what I'm up to. So we're going to carry straight on now from where we ended off at the last lesson. Now if you remember, we created our AI State Machine base class. It's not complete yet, we still have some functions to add to it, but we got quite a bit of the base functionality sorted and out of the way. And we also created our AI State class, which, although doesn't really contain an awful lot at the moment, it does define the interface that is going to be used by the state machine to talk to its individual states. And because our AI State Machine was abstract, we also derived this class from it, the AI Zombie State Machine, which if you look on the right here in the inspector, you can see is a completely empty class. It just derives from AI State Machine, so that we're able to drag that onto our AI Entity object and see its serialized properties show up in the inspector. So we can see now that the current state type enumeration is showing up, allowing us to choose the state that Jill is going to start off in. We also have slots where we can assign our target and sensor triggers, and we also have this really cool slider that allows us to set the stopping distance. What we're going to do first in this lesson is we're going to open up that Game Scene Manager script that we created in the last lesson and did nothing with. Now, to refresh your memory, if you look in the scene hierarchy, you can see we created this Game Scene Manager game object, and we added to that the Game Scene Manager script. Now that script doesn't exist in the AI folder, but in the parent scripts folder. So what we're going to do first is we're going to set up a dictionary in this game object and a few public functions or properties that's going to allow our state machine to register all of its colliders with that Game Scene Manager. The Game Scene Manager is going to act like a database for our AI state machines. You see, every single object in our scene, be it a collider, a script, a mesh, is all given a unique instance ID by Unity. It's just an integer that uniquely identifies that amongst all other objects in the scene. So what we can do is, in the start function of our AI state machine, we can call our Game Scene Manager for each of the colliders. We can get their instance IDs, and we can say to the Game Scene Manager, I want you to store this integer ID for this collider in a dictionary as the key, and as the value, I want you to store a reference to this AI state machine. So it means that any script anywhere in our level, if it detects that a collider has entered it, it can say to the Game Scene Manager, this is the ID of the collider that has entered my trigger. Can you please tell me if you have an AI state machine associated with it? So in order to do that, we're going to need to do a few things. We need to add a dictionary to our Game Scene Manager. We're going to need to add some functions so that any script anywhere in our scene can call the Game Scene Manager and do a query on the instance ID of a collider. I should say though that in that dictionary, because everything has an instance ID, you don't just have to be able to store colliders. You could store anything that you wanted to associate with an AI state machine. And finally, we're also going to need to make the Game Scene Manager a singleton so that there is only ever one of them in the scene, and any game object anywhere can get to that Game Scene Manager instance without having to query the scene, or without us having to painstakingly assign references in the inspector for every object that needs to access it. So let's do that now. I'm going to open up the Game Scene Manager in MonoDevelop, and I'm going to get rid of the boilerplate stuff. And because I'm going to store a dictionary in here, I'm going to need to use the system.collections.generic namespace. So I'll add that at the top of the file, like so. And then in my private members, we'll create a private member of type dictionary. And as the key, we're going to be using an integer because, like I said, we're going to use the getInstanceID method that all of Unity's objects exposes. That's going to return the unique integer ID of that object, which we can use to store in our database. And alongside that, of course, as the value, we're going to store an AI state machine reference, and I'll call this dictionary state machines. And of course, we'll allocate the dictionary as we normally do. So we're now going to need to create some functions that's going to allow our AI state machine to first of all register its colliders with this dictionary. And we're also going to need to create a public function that any script anywhere can call if it has the ID of a collider and it wants to fetch the associated AI state machine from this dictionary. So we'll make this a public method with a void return type, and I'll call the function register AI state machine. It's going to take two parameters. The first one is going to be the integer ID of the collider that we're registering with it, or any object It doesn't have to be colliders, but we're going to be using it for colliders. And as the second parameter, it needs to be a reference to the AI state machine that we wish to store in the dictionary. Inside the method, we just need to make sure that this key doesn't already exist in the dictionary. So we say if not state machines contains key, and then pass in that integer that we were passed as a parameter. So it means inside this conditional, we can say state machines key equals state machine, like so. So that's the only function that's needed for our state machine to register any colliders with this database. And you're going to see in a minute, we're going to add to the startup procedure of our AI state machine the process of calling this function twice, once to register the ID of its sensor trigger, and again to register the ID of its capsule collider. We don't need to register the target trigger because nothing else in the scene is going to care about interactions with that except the AI state machine itself. So now we need a public method that's going to allow any script anywhere to say to our game scene manager, I have an instance ID of a collider. Please can you tell me if there is an AI state machine associated with it? Because if there is, I want it returned so that I can talk to that zombie and set its various states. So we'll make this a public function that returns an AI state machine, and we'll call this get AI state machine. Simply going to take an integer, which is going to be, of course, the ID that we're going to use to look up into the dictionary. And we'll allocate a local AI state machine reference variable that we're going to store the result of the search in. I'll call this machine and set it to null by default. And then we'll use the dictionary's try get value function again. So we'll say if state machines try get value, and as the first parameter, remember, we pass in the key, and as the second parameter with the out parameter modifier, we pass in the variable that we would like to receive the result, which is our local machine variable. And you will remember that if that key doesn't exist, then the state machine's try get value function will return false, and this conditional block will not be stepped into. But if we do step in here, it means we have actually found the result. So we'll simply return it, return machine, and outside it means that it didn't exist, so we'll just return null. Like so. And I'm just going to put some comments on those functions. There you go. That looks a bit nicer. So we have the register AI state machine function now that's going to allow our AI state machine to register its colliders. And we've also got the get AI state machine function, which is going to be called from other trigger handlers that may be placed on objects throughout the level. Whenever there is an interaction that occurs on an object, it's going to want to know if the collider that has triggered that interaction belongs to a zombie. In other words, does it have an AI state machine? That's easy enough to do within the script. We simply just get the instance ID of the collider, and then we would call the get AI state machine function, and if it doesn't return null, then it's basically returned to us the answer, yes, it does belong to a zombie, and this is the state machine of the zombie that has entered your trigger. However, as we're going to have lots of these scripts handling lots of these interactions, we don't want, with every script we create, having to drag a reference to this game scene manager script. So we're going to make it a singleton. This means that only one game scene manager should ever exist in the scene. And what we're going to do is we're going to create a static instance member of the game scene manager class, which the first time it's invoked is going to search the scene for that instance and store a reference to it. And then when any script after that calls the property to fetch that instance, it's already going to have found that instance. It won't have to do any searching, and it can simply return it. So the first thing we're going to do is create a private static variable. Remember, this is going to be a member of the game scene manager class, not of any particular instance, and it's going to be of type game scene manager, and we'll call this instance, and we'll set it to null at startup. This instance is going to be used to store a reference to the only instance of the game scene manager that should exist in the scene. So now we need to create a public property, a getter, so that any script anywhere in our level can simply get to this instance and start calling the register and get functions that we've just created. So we'll create a public static property that returns a game scene manager object, and we'll call this instance without the underscore. And in the case where this is not the first invocation of this property, it needs to be a getter. So the very first time this instance property is invoked, our instance member is going to be set to null, in which case we need to do a very time-consuming search of the scene to find the only game scene manager component on a game object and store it. But we only want to do that if instance is null, which means that every other time that this property is called after the first time, we're already going to have cached that instance, and we can simply return the instance like so. So that is nice and quick. Like I said though, the very first time any script anywhere in our level tries to access this property, we do have to do the lengthy search. So we'll say if instance equals null, then instance equals, And we're going to use the find object of type function supplied by Unity, but this returns a generic object. So we're going to need to cast the result back to the correct type of Game Scene Manager, like so. And then we'll use the find object of type function, and it takes a type. So we'll say type of Game Scene Manager, like so. So as you can see, the very first time that this instance property is called, instance here will be null, and this code will be triggered that will search the scene for the very first instance of a Game Scene Manager that it finds on a game object, which we know is going to be this one and only instance here stored on our Game Scene Manager game object, and then it's just going to return it. But for every instantiation of this property after the first time, none of this will be activated because instance won't be null and will simply return the already cached instance of our Game Scene Manager. So that's all we need to do in the Game Scene Manager for now. Let's save that off and just check we haven't got any errors. And we haven't. All is good. So let's now drill back down into our AI folder, open up our AI state machine script, and add some code to its startup procedure that's going to register its colliders with our Game Scene Manager. So I'm going to add the code that registers the colliders of our state machine in its awake function. And remember, the colliders that we want to register are our sensor trigger, which is that great big sphere collider that's going to be causing lots of threats to be registered. And we also want the collider as well, which is the capsule collider that's on the object itself. Like I said, we're not going to register the target trigger because the target trigger is never going to be something that's processed by any external objects. We're going to handle any collisions between our capsule collider and the target trigger within the state machine itself by implementing on-trigger functions. So I'm going to move down into my awake function, and I'm going to say, actually I better make sure first of all that we have a valid Game Scene Manager in the scene, so you can see how I get that instance. So what I'm going to say is if Game Scene Manager dot instance doesn't equal null, and obviously if this is the first time that any script has tried to use that instance property, we saw just now that that's going to cause a search of the scene for that Game Scene Manager component. And then what we're going to do is we're going to say if we have a valid collider, remember this is our capsule collider, then we're going to say Game Scene Manager dot instance dot register AI state machine, and as the key we're going to send in the collider's ID. So we say collider dot get instance ID, like so. It's just a function that takes no parameters. Like I said, every Unity object supports that function, so that's going to pass in the unique integer ID of our capsule collider. And then of course, what state machine do we wish to register? This state machine. And we'll do the same with its sensor trigger. So assuming we have a valid sensor trigger reference, then we're going to do exactly the same again. But this time, of course, as the first parameter, we're going to send in the unique ID of our sensor trigger, like so. And of course, as the second parameter, we send in ourselves, this state machine. And you're going to see later how when we set up our zombies to have ragdolls, they're going to basically have a collider on every single body part, and this conditional here is going to be extended, and we're going to add code that is going to collect every single collider of every single body part and also register it with the Game Scene Manager. So every single collider on our zombie will be stored in that dictionary with its associated state machine reference. So I think the next thing we're going to do is we're going to add the onTriggerEnter and the onTriggerExit functions to this class. These are some of Unity's magic functions, meaning they'll be called by Unity. But when will they be called by Unity? Well, let's go back to our Unity editor, and we're going to get a message on this particular game object, which is, remember, is on the AI entity layer, when its capsule collider here enters the target trigger. That's the only time we're really going to get an onTriggerEnter and onTriggerStay message. All of the other collisions with our sensor trigger are going to be handled elsewhere. In fact, I use very much a push system, so it's the actual threats out in the world that push their sort of knowledge of themselves into the state machine rather than the state machine collecting them. So in our AI state machine itself, which is on the AI entity layer, all we're going to get notified about is things that collide with our capsule collider, and the only things that collide with our capsule collider are things on the AI entity trigger layer, and at the moment that is just our target trigger. So our onTriggerEnter function and our onTriggerExit function is purely going to deal with just the case where our zombie has arrived at its target. So let's go and implement those now. So I'm going to scroll down to the bottom of the source code, And I'll work on the onTriggerEnter function first, and I'll make this a protected virtual void so we can override it in the derived classes if we want to. And this, of course, is called onTriggerEnter, and it takes as its only parameter a collider. That's the thing that we've collided with. So when this function is called by Unity, this other collider here will be the collider of our target trigger. Now we need to make sure that it is actually our target trigger, because when we have multiple zombies in this scene, each one of those will too have its own target trigger, which will still be on that same layer. Therefore, this function is going to be called on our zombie, even if we entered into the target trigger of another zombie. So we need to make sure that other is actually our target trigger. So we'll simply return from this function if our target trigger is null, or if the other collider isn't our target trigger. Then we know whatever has generated this function is not a collider that we care about. We only care about one collider, our target trigger. So what do we have to do here? Well, pretty much nothing other than let the child state know that we have reached our target trigger. Then it can decide what it wants to do about that. So we have a method in our AI state base class called onDestinationReached. So that is what we will call to notify the child state. So I'll say if current state. We can't obviously pass a message to the current state if the current state is null, so we need to make sure we do have a valid current state, and we'll say current state onDestinationReached true, letting it know we have entered our target trigger. And I'll add a comment to that function that just lets us know. It says it's called by the physics system when the AI's main collider enters its trigger. This allows the child state to know when it has entered the sphere of influence of a waypoint or the last player sighted position, for example. So I'll also put a comment in there saying notify child state. So the next function we have to add is kind of the reverse of the onTriggerEnter function, which is the onTriggerExit function. And all that's going to do is call the onDestinationReached method of the current state, but passing false as the parameter. So I'm going to paste in that function so you don't have to watch me laboriously type it out. So as you can see, this is called whenever our character was in the target sphere but is no longer in the target sphere. And this typically happens when, let's say for example, the patrol state is running, and the patrol state will be notified when its destination has been reached by the onTriggerEnter function, because if it was heading towards waypoint 1, then our target trigger will be positioned at waypoint 1, and when we reach that waypoint we will penetrate the trigger. This method will be called, our child state will be called, and our patrol state will know that in its onDestinationReached function it has to fetch the next waypoint from the waypoint network and then call the parent state machine's setTarget function, which will then reposition the target trigger to the next waypoint in the list. And at that point Unity is going to determine we are no longer inside our target trigger. This method will be called, and the onDestinationReached method of the child will be called and set to false, so it has a chance to do anything in response to that. So we've seen how the AI state machine uses Unity's onTriggerEnter and onTriggerExit functions to trap any messages to do with its own capsule collider, which based on how we set up the collision matrix means that it's only going to get notified with collisions between this capsule collider and triggers that have been assigned to the AI entity trigger layer, which at the moment is just our target trigger. So how are we going to handle the AI state machine knowing about things that have entered its sensor trigger? Well, we're going to handle this on the sensor trigger game object itself. We're going to write a script here that traps the onTriggerEnter, stay and exit functions, and that script is going to essentially maintain a reference to its parent state machine, and whenever there's a trigger message it's going to filter it through and it's going to send it to the parent state machine. And then the parent state machine will then send that down to its child state. And we saw in the last lesson that our AI state class has this onTriggerEvent function, where we can tell it if there's been an enter, exit or stay event type and the collider that generated it. And we're going to do the same thing, use this almost exact same signature in our AI state machine. Let me implement that function now. So I'm going to create a public virtual so we can override it in any derived classes if we want to. A void return type, and we'll call this onTriggerEvent type, just like the child state. Remember, this function isn't going to be called by Unity. Unity knows nothing about this function. This is a function that's going to be called by the script that's on our sensor trigger when it's handling its trigger messages. So just like the child state version of the function, as its first parameter it will take an AI trigger event type, which we'll call type, and as its second parameter it will take a collider, which we'll call other. and that will contain a reference to the collider that has essentially entered our sensor trigger, although we haven't written that code yet. And inside the function, all it's going to do is just hand this message straight down to the currently active state. So assuming the current state isn't null, it's just going to say current state on trigger event. Oops, sorry guys, I've got that wrong. That should be on trigger event, not on trigger event type, just like the child state. And we just pass in the type and the collider. So as you can see, it just passes the message on to the state that's currently active. And this method is going to be called by the sensor script for on trigger enter, on trigger stay, and on trigger exit event types. So they're all just combined into a single function call that we control the calling of. And it also means that we can filter out anything we don't want the AI state machine to know about or care about inside the sensor script. So what we've seen really then is how our sensor script passes trigger information into the currently active state, even though they have no direct connectivity. So let's now do something with our sensor game object, which has that sphere collider on it. Because since we created it and added it to Jill, all we've done is assign that game object to the AI trigger layer, but we've done nothing else with it. In fact, since we created that AI trigger layer, I don't think we've even set that up correctly in the physics manager. So we should probably do that first by going to the edit menu, the project settings submenu, and then choosing physics to bring up the physics manager. And as you can see, the AI trigger layer is currently set to be collidable with every other layer. And at the moment, I'm going to turn all of those off because we've yet to create the layers that are going to be assigned to objects that our sensor is going to be sensitive to. But for now, just think whenever you see AI trigger, basically means objects that are sensors of zombies, because those are the only objects that are ever going to be assigned to the AI trigger layer. And you'll see later on that when we start creating aggravators, such as sounds that will aggravate the zombie, we're going to add triggers on them, and they're going to be on a special layer that is sensitive to the AI trigger layer. So too will the player be sensitive to the AI trigger layer, but we'll see more on that later. For now, what we need to do is just create a new script, add it to our sensor object so that it implements the on trigger enter, the on trigger stay, and the on trigger exit functions of mono behavior, which Unity is going to call whenever objects sensitive to the AI trigger layer enter our sphere. And those functions are then going to dispatch the message back up to the on trigger event function of the state machine that we just implemented. So I'm going to create a new script in my AI folder, and I'm going to call this AI sensor, like so. And I'm going to drag and drop that onto my sensor game object, and then I'm going to open it up in MonoDevelop. So the AI sensor script is going to have to store a reference to its parent AI state machine. And what we'll do is we'll have the AI state machine set this variable in its sensor, in its start function. So we'll go and sort that out a little bit later on. For now though, let's just create the variable that's going to store that information. So I'm going to create a private variable of type AI state machine, and I'll call this parent machine. Actually, parent state machine, just so I know exactly what that is. I'll set it to null. And I'll create a public setter for that, which the parent machine is going to need in order to set this member. So I'm going to call it parent state machine, and we only need a setter for this, and we'll say parent state machine equals value, like so. So I'm now going to go up to the start function of my AI state machine, and I might as well just do this at the top of the function. I'll say if sensor trigger isn't null, then we'll allocate a local variable of type AI sensor, which remember is the name of our behavior, and we'll just call this script, and we'll say equals sensor trigger get component, and we're looking for type AI sensor. So what we're saying is if our sensor trigger variable has been assigned a valid reference to a sphere collider, then we're going to say to that sphere collider, can you please give me, if it exists, the AI sensor component that is on your game object? And if one exists, script will not be null. So then we can say script dot parent state machine equals this. And we've just stored a reference to ourselves, this AI state machine, inside that sensor script, so that the sensor script is now going to be able to, in response to getting trigger messages, dispatch a call to this on trigger event function. So let's now call up our sensor script. Actually, I don't think we need the start function or the update function. I think all we need to do is implement the on trigger functions. And I've just pasted all of these in just because they're so simple. As you can see, if we look at the on trigger enter function, when this is called by Unity, it's going to pass in the collider of the object that has entered our sensor trigger And assuming we have a reference to the parent state machine, we're going to call its onTrigger event function, passing in as the type of event the enter type, and we pass in the collider. And the other functions, the stay and the exit variants, are exactly the same, except when they call the onTrigger event function of the state machine, they just pass in AI trigger event type.stay and AI trigger event type.exit respectively. And that is our sensor script done. So now's a good time to pause the video if you want to copy that and type it in yourself. So I think what we want to do now is add a couple of extra properties to our AI state machine so that any calling object can ask the state machine to give it the world space position and radius of its sensor trigger, because we saw in the last lesson that our AI zombie state machine is eventually going to have properties such as hearing range and sight range, and when those calculations are being performed, they're going to need to know the position and the radius of the sensor trigger to see whereabouts within the sphere that object is and whether it truly is a threat. And getting the position and radius of the sphere is not as simple as it might seem, because not only do we have the center offset from its parent game object, but both that center offset and the radius may have been scaled if any game object in its hierarchy, in other words, if any of its parents, direct or otherwise, has any scaling factor other than 1, then these are only really telling us in the sphere collider what the local offsets are before that scale. If I click on the sensor game object's parent, for example, and scale it up, you can see that changes the size of the sphere trigger. But if we look at the sensor, its radius hasn't changed. So we need to calculate what that radius is once it's been scaled by all the scaling factors of the game objects above it. And the same too is true for the position, which this center offset here of 1.6 needs to be scaled if we've made its parent game object, or the one above that in the hierarchy, twice as tall, for example. That offset's no longer going to be 1.6, it's going to be twice as high as that. So we need an easy way so that any script can say to our AI entity, I'm going to do some calculation based on your world space size and radius. So those are the properties we're going to implement now. So I'm going to call back up my AI state machine, and I think as these are properties, I'm going to kind of put them up near the top of the class underneath my public properties section. And the first property I'm going to create is going to be the one that calculates the world space position. So this is going to return a vector 3, and I'm going to call it sensor position, and all we need is a getter for this, and we should do a check really just to make sure that we have a valid sensor trigger. So we'll say if sensor trigger equals null, then just return as the position vector 3.0. Otherwise, we're going to first of all get the position of the sensor trigger's game object. So we say vector 3 point equals sensor trigger dot transform dot position, and then we need to adjust each of the components of this point, factor in the scale that may have been applied to this game object from the scaling of any of its parents. And the transform component has a property called lossy scale that allows us to get this information. So we'll start with the X component first. So onto the X component of our point, we will add the sensor trigger's center point. Remember, that's this center offset here, which is 1.6 locally, not taking scale into account. So if we didn't take scale into account, then irrespective of how we've scaled up the parents, we would only ever be adding 1.6 on, which may not be correct. But then we multiply that center offset by sensor trigger dot transform dot lossy scale dot x, and the lossy scale vector is basically just something that is calculated as the hierarchy is being concatenated, as it works its way down the hierarchy, and when we get to the child, it tells us what the basic scale is that's been applied to it throughout the entire traversal of the hierarchy. So that's exactly what we want. And then what we'll do is we'll do exactly the same for the Y and Z components, remembering of course to change the components to the correct type. Oops, actually I've made a mistake there. Obviously, because I'm doing this on a per component basis, just to make it easier to see what's going on. And then, of course, we just return our newly scaled center point of our collider. Now, calculating the concatenated scale of the radius is a little bit more tricky, because if we click on our sensor game object, we know, of course, that the radius is just a float. But its transform, and in fact, any of its parent transforms, can have a different scale on the X, Y, and Z axis. So if I scale down the X component, you can see that doesn't affect the radius at all. But if I scale up the Y component, you can see it grows to contain the y component. But then if I scale up the x greater than the y, it seems that the largest component out of the three components is used to scale it. So we'll do the same thing. Okay, we will take whatever the maximum scale is of that lossy scale that we get from the transform, and we'll use that to scale the radius. So what I'm going to do is I'm actually just going to paste this function straight in so we can get straight down to studying it. And as you can see, it's a public float property called sensor radius. It's a getter only, and we first say if the sensor trigger hasn't been assigned, then just return 0 for the radius. However, if the sensor trigger has been assigned, then the first thing we do, actually let me just move that over so it's a bit easier to read. I calculate the first radius value by saying I want to take the max of the sensor radius multiplied by the lossy scale x component and the sensor trigger radius scaled by the sensor trigger lossy y component. So it will be whatever is the largest using both the x and the y components of the lossy scale. But of course we haven't factored in z, so once we've got the largest stored in radius of x and y, we then do a final max test between our radius, which remember is the max between the x and y lossy scale, and sensor trigger radius multiplied by lossy scale.z. So we're just making sure that we take whatever is the maximum value from scaling our sensor radius with lossy scale x, lossy scale y, and lossy scale z. And then of course we return whatever that maximum value is. I think that should generate exactly the same result that we see in Unity's scene view when we change the scale of its parents. So I'm just going to stay on this section of the code for a moment so that if you're following along with me, you can pause the video and type this in. Gives you a place to pause. And then what I'm going to do, if I bring up the AI state class, you can see there's still some functions here that we haven't set up messaging for in our AI state machine. We haven't made a function yet that calls onAnimatorUpdated, and we haven't done one that calls onAnimatorIKUpdated. So I think those will be the final two event handlers that we have to handle in our base AI state machine class. So let's move down to the bottom of the code and add them there. Now we saw, I don't know how many lessons ago it was now, maybe 2 or 3, that if we have a mono behavior on a game object that has an animator, and that animator is using root motion, then in order to stop that root motion being automatically applied, but instead have a place where we can do something with that root motion ourselves, we just have to implement a function called onAnimatorMove. So we're going to do that now in our AI state machine. So it's going to be a protected virtual void called onAnimatorMove. And you'll remember this function took no parameters. And there's nothing we want to do with the root motion inside our base class of our AI state machine because we don't know what the current state might be wanting to do with it. So what we're literally going to do is just dispatch that event straight down to our currently active state and call its onAnimatorUpdated function. So in our AI state, that onAnimatorUpdated function is exactly the same to us as the onAnimatorMove function would be in a mono behavior. It allows us to fiddle around with the root motion and do what we want with it. So going back to our state machine, that's going to be a pretty easy function to implement. We just say assuming the current state is not null, then we say current state onAnimatorUpdated, like so. And remember, this is one of those magic functions that Unity will call on a mono behavior if it's implemented once the root motion has been calculated but before it's been applied to the game object. So we want to trap that here, and we don't want to implement this method in all of our states, so otherwise that function is going to be getting called in all of the states, even the ones that aren't active. So that's why I trap it once in the state machine in this function, and then I just pass it to the currently active state using our own version of that function called onAnimatorUpdated. Now I'm going to implement another function of mono behavior which we've never seen before and we won't do anything with yet, but we'll see it being used later when we start implementing our states. It's going to be a protected virtual void, and it's going to be called onAnimatorIK, IK being short for inverse kinematics. And this function is called by Unity just before Unity is about to update its internal IK system. So this is the place where we can jump in at the last minute just before this happens and alter the IK goals and their weights. And this function takes an integer parameter, which is the layer that it's being called for in our animator controller. So I will call this parameter layer index. Let's be honest, we have no idea how to use this yet. I haven't talked about it, and we will talk about it later on. But I don't want to get distracted with this discussion now, because all the base class is going to do is just notify the currently active state that if it wants to, now would be a good time to contact the animator and tell it to set some of its IK goals. And if you don't know what I'm talking about when I say IK goals, don't worry about that either. Of course, the function that we implemented in our AI state class was a function called currentState.onAnimator IK updated, like so. Now, we've also seen in previous lessons that when we're using a NavMesh agent, by default the NavMesh agent will automatically update the position and the rotation of the game object. But we also saw how we can tell the NavMesh agent that we only want it to update the position, or we only want it to update the rotation, or we want it to update none of those things. Now, I think we're pretty much going to be using a system in most states where we want the NavMesh agent to update the position, but we'll take care of updating the rotation, either by making the player face in the direction of the target, like we saw a few lessons ago, or by using the root motion that is given to us via the animator. But either way, it would be pretty nice if any of our states could say to the AI state machine on a per state basis, I want you to configure the nav agent in this particular way for this particular state. So we're going to create a function that's going to allow our states, or indeed any object that wants to talk to our state machine, to do that. So we're going to create a public function. This doesn't need to be virtual because we'll never want to override this. It does something that's so simple. We either want to use it or we don't. So it's a public function with a void return type, and I'm going to call this nav agent control. And it will take two booleans. The first boolean will simply describe whether we want the nav agent to update the position. So we'll call that position update. And of course the second one will be whether we wish the nav agent to control the rotation of our game object, like so. Then inside the function we'll just say if we have a valid NavMesh agent, which remember we've cached inside our NavAgent class variable, then we will say NavAgent.updatePosition equals position update, and NavAgent update rotation equals rotation update. And that's all that function has to do now. So any of our child states, when we enter them, can say, hey, I want the nav agent to behave in a certain way with respect to my game object, and we can configure this on a per state basis. So I think I'm going to add some comments to all of these functions that we've just written. There you go, that looks a little bit nicer, doesn't it? Certainly help you guys out when you download this this script. Makes it a bit more readable. So we just have one more little system to set up, and then our AI state machine base class will be complete. And thankfully we can then move on to creating our actual derived zombie behaviors. And the system we're going to create is going to allow our animator to tell our AI state machine on a per state basis whether root motion or root rotation from the animation file should be used to position our transform. To understand why we need this, cast your mind back to a few lessons ago when we had Zombie Jill here running around the level. You will recall that when we assumed the use of root motion and root rotation all the time, we had a situation where sometimes Jill wouldn't be able to get the angle that she needed based on the animations in her blend tree to get to the target, be that the player or another waypoint. And we saw how we could make Jill more agile by saying that when she was in a locomotion state, we would throw away the root rotation and would rotate Jill ourselves so that she was facing in the direction described by the desired velocity of the NavMesh agent. But we also had to be aware that if Jill had to make a very steep angle turn, then we would see her spin on the spot. So in cases where we wanted to do that, what we would do is transition her into a turn on the spot animation, and in that situation, when the turn on the spot animation clip was playing, we did enable root rotation so that she didn't look like she was sliding. Now in that early demo we were able to hack this into our demonstration code quite easily, because all we had was a locomotion state that didn't use root rotation and a turn on the spot state that did use root rotation. But we're going to be designing a much more complex animator now with multiple layers and quite complex animation state graphs on each layer. So we're going to need a system that's much more generic, a way for us to say to the AI state machine, this clip currently playing wants to use, for example, the position from the root motion but not the rotation, or vice versa, or both. So how can we do that? Well, fortunately, there is a new script type that was introduced with Unity 5 called State Machine Behaviors, and they really are quite wonderful. If I call up the Unity documentation on state machine behaviors, you can see in this image here that a state machine behavior is much like a mono behavior. But whereas mono behaviors are added to game objects and are seen as components, state machine behaviors are added to states within the animator. This allows us to add any number of custom scripts to a single state in the animation graph, and in our case we can have a script on each of our states such that when that state is transitioned to, communicates with the AI state machine and says, hey, I want you to turn on root motion, or I want you to turn off root motion. If we call up state machine behaviors in the Unity scripting reference, you can see that the interaction happens much like with a mono behavior when Unity calls several handler functions. So you can see, for example, there is an onStateEnter function, which if we implement, Unity will call when the first frame of that state is about to be executed, much like we have the onTriggerEnter function. There's also the onStateExit method, which is going to be called by Unity when we're just about to transition away from that state and it's the last update. We also have the onStateUpdate method, which is analogous to Unity's onTriggerStay method. It's going to be called every single update of that animation except the first and last updates, which of course are handled by the onStateEnter and the onStateExit methods. And it also has the onStateMove and the onStateIK methods, which are analogous to mono behaviors onAnimatorMove and onAnimatorIK methods. So we have handlers that allow us to tap into each point along the animation timeline and do things. And up above here you can also see there's public functions to handle when we actually enter the state machine and exit the state machine, and this is going to be more useful when we're using an animator that actually has sub state machines built within a given layer. Now we're not going to be doing that in this zombie state machine, I don't believe, but we will be using these probably later on when we design the state machine for our first person ARMS system. So it seems pretty easy, right? What we can do is we can implement the onStateEnter method of one of these state machine behaviors, and when this method is called, we can say to the state machine, hey, I want you to enable root motion, and when it exits it, we can say, hey, I want you to turn off root motion. And we can also define some variables that will show up in the inspector, which is again another really cool thing about state behaviors. They're going to have their own inspectors, so we can create a very generic root motion configuration script that just has two Boolean variables that are exposed in the inspector, so that in our state machine we can select a state and we can say, hey, I'm going to turn on root motion and turn off root rotation for this state. However, there is something we need to be aware of. Our state machine behavior is obviously going to need to talk to our AI state machine. However, the AI state machine is an instance that exists in the scene, and we can't store references to objects in the scene in the inspector of our state machine behavior. And the reason for that is that unlike a mono behavior that we drag into the scene and place on a game object, which then exists as an instance in the scene, the animator on which the state behavior lives is an asset. It doesn't actually exist in the scene until we actually press play. Because you'll remember, of course, we only create one animator controller, but we assign that to the animator of various different zombies. When we press play, we can think of the animator component as being like a prefab, which Unity then instantiates at runtime all of the different instances of. Therefore, the instances of the state machine behavior scripts that we've added to our animator also don't exist until we press play at runtime. So we can configure the inspector fine for static stuff, for setting variables like integers and booleans, but if we want to store a reference in our state machine behavior to our AI state machine, we're going to have to do that another way, and we're going to have to forge that relationship at runtime. So let's start the process of implementing this by adding two new variables to our AI state machine that are going to log the requests for root position and root rotation from the animator. Now you might think, well, we can just make these two booleans, but you see we can't. Instead, we're going to have to implement a reference counting mechanism. You see, we have to remember that the animator is multi-layered. So let's pretend that we had an animation state that was playing on the base layer that has said I want both root position and root rotation to be used from the animator. Using booleans, it would contact the AI state machine and set both these booleans to true. But let's say then that some event happens in the game, such as a cinematic sequence, and that triggers a parameter in the animator that causes the cinematic layer in the animator to override what is currently playing on the base layer. But let's also assume that in order for the animation clip on the cinematic layer to play properly, it doesn't need to use root rotation. So it contacts the AI state machine and tells the AI state machine to set root rotation to false. However, when that animation clip in the cinematic layer has completed and it's over, and that layer is now turned off, we're back in the base layer, which, remember, is the animation clip that wanted to use both root position and root rotation. When we go back and that clip is still playing, root rotation has then been turned off and the animation is not playing correctly. Trust me, I made this exact same mistake when I implemented this system to begin with. So what we will do is we will implement these two variables as integers, and our individual animation states will essentially request both root position and root rotation that will cause these integers to be incremented. Therefore, if we had a animation on the base layer that had requested, say, root rotation, then the root rotation reference count would be 1. If we then moved up into the cinematic layer, because it was overriding the base layer, that animation clip doesn't want root rotation, so that would decrement that count by 1. So the root rotation variable in our AI state machine has now been set back to 0. However, when the state machine behavior on the animation clip in the cinematic layer exits, it will once again add on that reference that it decremented at the start of its behavior, setting it back to 1 again, so that when the base layer animation clip gets focus again, it's set to 1 and we've got root rotation as it expects. So basically, any animation clip in our animator that, say, for example, wants to have root motion, in its onStateEnter function will add that reference, but then in its onStateExit function will remove that reference. And the same will be true in reverse for states that don't want root motion. On their onStateEnter function, they will essentially decrement that reference, and on their onStateExit, they will add it back on again. So we always keep track of whether some state somewhere playing in a layer is requesting root motion. Of course, this isn't going to help you out if you design the layers very badly in your animator. If you have a situation where you have two animation clips playing at the same time on both layers that both have non-zero weights, and one of them wants, say, root rotation and the other one doesn't, well, then you're gonna get root rotation in that sense, and the other animation will have to suffer. But you shouldn't design your animation tree in any way that would be an issue. So let's now add those two protected integers to our class. I'm going to paste them in, save me typing them. This is what they look like. The first one is called root position reference count, or ref count, and the second one is called root rotation ref count. And I set them both to 0 initially, which means by default we're not requesting any root motion at all. And then what I'm going to do is implement a public function that our state machine behaviors can call to increment or decrement both of those reference counts. So this is going to be a public void return type, and I'm going to call it add root motion request. And it's going to take two integers. The first one will be root position, and the second one is called root rotation. And remember, these will either be 1 or -1. Okay, they can be negative values as well, which means they're going to decrement the reference count. And then we say root position ref count plus equals root position, which, remember, if root position is a negative value, that will subtract it. And root rotation ref count plus equals root rotation, like so. And I'll put a nice little comment in there, like so. And then I think what I'm going to do is I'm going to add two properties that our child states can query to test whether root position or root rotation should be applied. So basically just testing whether these values are greater than 0. So I'll put those right up the top there in my public properties block. So this is going to be a public Boolean return type, and I'll call the property use root position. And this just needs a getter, and it will simply return the result of if root position ref count is larger than 0. And then, of course, we'll add another public property to do exactly the same, but this time to query whether the root rotation reference count is larger than 0. So return So I think we've pretty much implemented everything we need to put in the base class. I may be wrong about that, we may need to come back later, but we've certainly put everything I can think of in it for now. We have a means for our state behaviors in our animator to request from the AI state machine that it increments or decrements its root position and root rotation reference counts. And we also have two public properties so that our child states or any object can query whether root rotation or root position should currently be getting applied. So I'm going to save that off, and then what I'm going to do is I'm going to go and create our state behaviors that we can then add to the states in our animator. So back in the Unity editor now, inside my AI folder, I'm going to create a subfolder, and I'm going to call that State Machine Behaviors. And I'm going to drill down into that, and I'm going to create our first state machine behavior. Now, although we know we need to already create a state machine behavior that's going to configure the root motion on a per state basis of our AI state machine, it also seems to me that we may down the line want to create other state machine behaviors that interact with our state machine in a different way. But there is going to be some common link here, and that is irrespective of the state machine behaviors that we create that are going to manipulate the properties of our AI state machine, all of them are going to need to store an AI state machine reference. So what I'm going to do is create a very simple state machine behavior base class that literally just contains that reference to an AI state machine. And then what I can do is I can derive my state machine behaviors from that, and you'll see why that's important in a moment when we get to the point where we start setting that reference at runtime. So I'm going to create a new C# script, and I'm going to call this AI state machine link, like so. Then I'm going to open that up in MonoDevelop. And we want to get rid of all this boilerplate stuff because this pertains to mono behavior anyway, and our AI state machine link class isn't going to be derived from mono behavior at all. It's going to be derived from state machine behavior, like so. Now this is going to be a really simple class. All it's going to do is store a reference to an AI state machine. And the nice thing about having this base class is we know that however many scripts we create that are derived from this, they're all going to need to store a reference to an AI state machine. And in a moment when we go back to our state machine and we add the code that's going to store in this script the reference to the state machine, then we know that irrespective of what this script actually is, we can set that link up very easily for any behavior that's on our states and in our state machine. But we'll see how to do that in a moment. For now, we're going to create a private AI state machine reference, and I'll call this state machine. And we also want a public property that's going to allow our AI state machine to set this for each of its individual state machine behaviors. So we'll make this a public AI state machine, and we'll just call this state machine without the underscore, and it just needs a setter, and we'll just say state machine equals value. Like so. That's all this thing does, just stores a reference to a state machine. So now if I go back to the editor now, we're now going to create our derived class from this, and I'm going to call this root motion configurator. Dun, dun, dun. And I'm going to load that into MonoDevelop. Going to remove all the boilerplate stuff because this is not going to be derived from mono behavior. And of course this one is actually going to be derived from our base class, which is AI state machine link. So the first thing I'm going to do is I'm going to add two members that are going to show up in the inspector that are going to allow me to configure what I want to happen to the AI state machine's reference counts when this state is active. So I'm going to serialize this field so it's in the inspector, and it's going to be a private int, and it's going to be called root position, and we'll set it to 0 by default. And I'm going to create another one, once again a private int. As you've probably guessed, this one's going to be called root rotation. And like I said, this is just going to allow us to basically specify what we wish to happen to the reference counts, how we want them to be incremented or decremented. Now in pretty much any case that I can imagine, these values are either always going to be set to 1 or -1. I can't imagine an instance when we would want to assign this script to a state and, for example, have the root rotation incremented by 2 or 3 instead of 1. So we've got that choice if we should ever need it, but I can't imagine it ever being needed. So the first thing we need to do now is we need to implement the onEnterState method that we looked at in the manual earlier. And it takes a very specific function signature like so. on state enter, it needs to be override public with a void return type, and as its first parameter it takes the animator that this is being called for, and it also is passed an animation state info structure which contains information about the animation state that is currently running. So that can be interesting, even though we're not going to use that here. And it also passes the index of the layer in the animator that this state is currently on. None of this information we need to know at the moment. And I've just had a thought. I'm going to just go back to my AI state machine link script a minute. That doesn't need to be private. That needs to be protected because we want our derived classes to be able to access the state machine. What a fool. So inside this function, all we're going to do is we're going to say, assuming we have a valid reference to an AI state machine, then we're going to call its add root motion request method passing in these two parameters. And this is what that looks like. Assuming we have a valid state machine reference, and we pass in root position and root rotation, which as we've discussed will usually be either 1 or -1. So let's now implement the onStateExit method, which has to undo whatever the onStateEnter method did. So the function signature for onStateExit is exactly the same as for onStateEnter, so I'm just going to do a copy and paste there. I'm going to change the name from enter to exit. And all I have to do inside the function is, instead of passing in root position and root rotation, I just pass in minus root position and minus root rotation. So if root position was 1, then when we enter the state, we would add 1 to the reference count. And when we exit the state, we would subtract 1 from the reference count. And that, my friends, is our root motion configurator done. So what we need to do now is go back to our AI state machine script. And we need to go up to the start function, and we need to add some code that is going to get all of the behaviors on the animator and set its state machine reference. Unfortunately, Unity's animator component has a function called getBehaviors that allows us to do just that. We can call getBehaviors and tell it to give us an array of all of the behaviors that are derived from AI state machine link. So that's what we're going to do. Now I am going to do this in the start function, which is recommended, not the awake function, because there is a chance in the awake function that the animator and the various state machine behaviors may not be set up and ready to use yet. So at the bottom of the start function, I'm going to allocate an array of AI state machine links, like so, and I'll call this scripts, and then I will use the animators get behaviors method, passing in as the type of behavior that we wish to fetch any behavior that is derived from AI state machine link, like so. Now I should handle the case where for whatever reason we've erroneously not put an animator component on this object, so I better just wrap that in an if animator conditional. And assuming our animator controller does have some state machine behaviors assigned to its animations that are derived from AI state machine link, then this scripts array, shouldn't be an underline there, is going to contain all of the scripts. So all we have to do now is iterate through them. So we'll say for each AI state machine link script in scripts. So for each iteration of this loop, we're going to be processing one of the scripts, and it's going to be stored in this script variable. So what we have to do is say script dot state machine, which remember is that public setter property that we created in our AI state machine link class, and we have to say state machine equals this. And that's it. We've now set up that relationship. And like I said, the reason why it's really cool that we have the AI state machine link base class which stores the state machine reference is that even if we create other state machine behaviors that do other things to our AI state machine, this code will find them all and set the state machine reference for all of them. So really, really cool. So the problem at the moment is we're not going to see anything happening. So we're not going to know whether this is working. So what I'm going to do for the moment is I'm going to go back to my root motion configurator script, and in the onStateEnter method, I'm just going to temporarily wrap that in the if state machine block. And then what I'm going to do is I'm actually going to output the type of the state machine. So if our state machine isn't assigned correctly, then this won't even be executed and nothing will be output to the console. But if it is executed correctly, we should see it output AI zombie state machine, which is the actual type of the state machine that we have added to Jill. So I'll say debug, so I'll say debug log state machine dot get type to string, like so. And if I go back to the editor and select zombie Jill, you're reminded that it's actually an AI zombie state machine script that we added that is derived from AI state machine. So we should see AI zombie state machine get printed to the console window when this runs. But that's not going to happen yet because we haven't added the state behaviors to any of the animation clips in our animator. So with Jill selected, select the AI entity game object in Jill's hierarchy and call up the animator window. So we're seeing the animator for Jill. And what I'm going to do is I'm going to select the zombie idle state. And you can see we now have an add behavior button in the inspector of our animation states. So if I click that, you can now see that our animation states are listed. I'm going to choose root motion configurator, and then what I'm going to do is set root position and root rotation to 1. And if I call up the console window now and press play, we should see, hey, there you go, AI zombie state machine was output. And remember, that is actually output from the onStateEnter method of our root motion configurator. So we know not only is this being executed, but we also know our state machine is being correctly set because it correctly identified its type. So let me get rid of that stuff now. And going back to the editor, of course, we can decide to do that on whichever states we want. So I'll select the turn left animation and I'll add root motion configurator to that as well. And we'll set root position to 1 and we'll set root rotation to 1 as well because we want that on both of our turn on the spot animations. So I've added a root motion configurator to our turn right animation, like so. And our locomotion state, we don't need to add one of these scripts to because we definitely don't want root rotation being set, but we do want root position being set. So I suppose to be well behaved, we should add one of these anyway and set root position to 1 and root rotation to 0. And the same is actually going to be true for crawling, although we haven't dealt with the crawling behavior yet. We're going to treat it very much the same as any locomotion behavior, which means that we want it to use the root motion for its position that is going to be used to set the velocity of the nav agent. We want to sort of turn the zombie on the spot because we don't have any turning whilst crawling animation, so we've got no choice. We have to spin that puppy on the spot whenever we wish it to change direction. So I'll add a root motion configurator to that. Once again, root position equals 1, root rotation equals 0. Now remember, you might be thinking, well, why don't we set root rotation to -1 if we wish to turn off root rotation? But we don't have to do that because if, for example, we're in the zombie idle state, you can see root position and root rotation is set to 1, but as soon as it exits that state, they're going to be set back to 0 again. When we go into the crawling locomotion, it's going to set root position back to 1 again, but root rotation will not be set to 1, it will be left at 0. So we do need these root motion configurators on all of our, essentially our locomotion states on the base layer. So the only time we really need to use negatives is when on an additional layer, such as a cinematic layer or an attack layer or a death layer, we know that in the base layer there might be root position or root rotation being used, and we want on that layer to cancel it out. But you'll see how all that's used later. So I think that's pretty much all we're going to do for today. Time has moved on. We've got quite a bit done, including our introduction to state machine behaviors, which we're going to be using not only throughout the zombie animator, but also our first person arms animator when we get around to that. So thanks for listening, guys, and I will see you in the next video. Bye bye now.